that the operating system can see. And then you have the user applications that run on level 3. And because you can run any application on your operating system, you don't want, in most of the time, you don't want that application to interfere with the kernel. So the idea is that if multiple users run their processes on an operating system, the kernel is safe because the user itself cannot go through the kernel and interfere with another user or another application. So in this privilege escalation attack, someone can exploit a software bug or a design flaw, typically to increase privilege in the application. So in a very typical scenario, imagine that you have a vulnerable program that the kernel is loading and then passes control and the vulnerable process starts executing. And because of a design flaw or a buffer overflow, the user can take over and jump into kernel code and execute a malicious application. We will try to do the same thing, but using the hardware itself, not using an exploit in the process. So just to mention, there are two types of privilege escalation. The one I mentioned is you are running a user application and then you gain privileges and you go into the kernel. And there is also horizontal privilege escalation where you are, as a user, are able to attack a resource of another user. Essentially, you are at ring 3 or level 3 in the previous slide. Then you jump to level 3 of another user, essentially. Okay? So going back to those rings, horizontal means I am at level 3 and I'm Nectarios, and then I jump to level 3 of another user and attacking another process, or I can jump from level 3 and attack the kernel, which is level 0. Okay? And there is a very long record of such attacks on Windows. There are many buffer overflow attacks that I mentioned before. In Linux, there is the core dump attack. And also in the web, if you can extrapolate the same idea, you can have cross-site scripting attacks that can happen. This is the same idea, of course, not in the same setting. Now, this is another very important prerequisite. In order to be able to launch this privilege escalation attack on the processor, you need to have a particular hardware structure. You need to have the ability of process space IDs. So here's the idea. When you have a processor, in order to avoid the expensive translation look-aside buffer flashing, a translation look-aside buffer is a hardware cache memory that allows you to store the virtual memory address translation. Because modern operating systems use virtual addressing, a translation look-aside buffer allows you to store frequently used pairs of virtual addresses to physical addresses. But every time you do a context switch, a context switch is when you change from one process to the other. And because every process has a different virtual space, you need to empty this cache memory. You need to delete everything from the translation look-aside buffer, and this is an expensive operation. So since processors are storing the process ID in the translation look-aside buffer, this process ID is used to match the entries in that buffer so that it prevents you from deleting every entry in that table. So let me give you a visual example. So here we have a processor, and on the left, on the top left, we see that we have a space identifier that is several bits, and this tells us essentially which process this row belongs to. Okay? We are using a translation look-aside buffer that has entries for multiple processes. the idea is that instead of using a translation look-aside buffer for one process and then deleted everything, and then filling the buffer again for the other process, we just have more entries, and every entry is tagged with the process space, essentially. Okay, now the second entry is the virtual page number. As you can see on the top left of that picture, it says virtual page number. And there is also the page offset, and essentially this table translates a virtual page to a physical page, all right? So using this idea of having address space identifiers and matching every identifier to a process, you don't have to delete every row in the table every time you do a context switching in the operating system. You can just use other entries in the table, match which rows are applied to a particular process, or just delete the least recently used entries in the table. So you don't have to empty the entire table. That's the idea. And both those prerequisites, the prerequisite of having rings and the prerequisite of having identifiers in the translation look-aside buffer, is something that exists in real processors. So the Intel x86 processors, they have these 4 privilege levels, and they also have the page global enable flag, which is a very simplistic way of keeping entries in the translation look-aside buffer. There is also the alpha processor, where we have, again, 4 privilege levels, and we have a longer value called address space number that is used to identify the particular process. So the attacker that I'm going to show you in the next few slides is actually applicable, because real processors have these hardware structures to enable the attack. Right. So because that was heavy, let's spend a minute to relax, and I'm showing you a picture that will calm everybody down. You just turn on your microphones and talk to me or ask questions, but relax for a minute so that we can dive into the rest of the technical details of how the Trojan works. Right? Does anybody have any questions that you would like to ask at this point?
I just want to clarify my understanding of the TLB that you're describing. So you're saying
Yes.
to minimize the overhead of flushing out the TLB rather than just maintaining one process's virtual memory mapping. It's longer, contains multiple processes, and the processor's checking that the active process's PID versus sort of the PID stored in the different sections of the TLB.
That's the idea, yes. Essentially you have a cache memory, and each row in that table starts with, let's say, a process ID, and then it says this virtual address maps to this physical address. So if you didn't have this process ID, every time you do a context switching in the operating system, you have to flush the TLB and populate it again. So that's very inefficient. So the idea is that you make it longer every row, and then you have a tag saying this is the process ID that's using this virtual address. And because each process has its own virtual space, unless you have this tag at the beginning, you don't know the actual process that uses this row. So if you don't know what process is using each row, you have to empty the entire table. But now modern processors, they have this tag, and you only delete the least recently used entries, or you can have your own policy when you design your own processor. But the idea is that you don't have to delete every entry in the table.
Okay, yeah, so you're just storing significantly more data in order to get around having to flush it out constantly, yes. And you're trusting that the processor will do the right thing always because it's the processor.
So as we will see in the next few slides, there are ways that we will exploit that. But the idea is that if you have a trustworthy processor, you trust that it will give you the right translation for the right address space or the right ID. That's the idea. Okay,
great, thanks.
All right. So, okay, so I guess the minute is up. Let's mute the microphones again, and let's move forward to additional details. Okay. So this particular attack has been implemented on the design of a particular processor, Alpha 21264. This is an out-of-order 13-stage pipeline with hybrid branch prediction. It's actually, we didn't actually do it on real hardware. We simulated the processor. So there is a simulator called GEM5 that was used to demonstrate the attack. And the underlying operating system was Linux kernel 2.4. And in this attack, we used a synthetic workload and spec 2000 benchmarks. So let's see the attack. Now this is, I have been talking about this attack for several slides, but I haven't showed you the attack. So this is the attack. Going back to the original translation Lucasite buffer, the attack is to insert a delay to the most significant bit of the address space number. So we introduce this at the foundry as a delay fault. Essentially, we make the wire react slowly to a signal. As you can see on the left side of the image, this delay fault is the most significant bit, and it will make the processor choose which row on the table we are interested in. And if the processor does not read quickly enough the signal and reads an incorrect value in the most significant bit, it will select a different row. Okay, so selecting a different row can have a devastating impact, as I will explain. But adding the delay fault is generally straightforward when you control the foundry and you control the mask. You can just change the wire size or the gate size, or you can try to squeeze an extra buffer there to increase the delay. Okay, so if the MSB of the address space number fails to capture the change, instead of, for example, seeing the address 128, it will see all zeros. And that's the number that will be used in the next cycle when we select the row in that table. So essentially, we are forcing the next instruction to see a different address space, to use a different translation space through the translation Lucasite buffer. And by carefully choosing the user process, we can make it choose the actual kernel, because the kernel is using ID 0. So if we can force something like 128 to go to 0, then we are actually using the kernel space to in the next instruction. Now we have to be very quick, because this window that we're getting is not going to hold for a lot of time, and also we have to be very lucky. Okay, this attack does not work all the time, but it works with a certain probability boundary. So to actually implement the attack, you not only need to have the wire delay in the processor, this wire delay that I showed here on the left-hand side of the picture, you also need to have an actual user application as your payload. So how can this happen? You have a malicious process that tries to write an instruction in a special kernel function. In the alpha processor, this is what we call PAL code. PAL code is privileged code that is used in the operating system. And what you are trying to do is you are trying to insert a malicious instruction in that space that should be allowed because you just swapped the memory space in the translation look-aside buffer. So the first thing you need to happen is to manage to change the line here through the delay. The second thing is immediately after you have access to the kernel memory space because of the incorrect translation in memory, then you try to put a return instruction. Okay, so as soon as the corrupted kernel function is invoked, it will see the malicious modification that you did in the memory space, and it will return to your own code. Okay, so because the system was in kernel space, now you return to code with the privileges of the kernel. So that's a privilege escalation attack. Now, when you have an attack that doesn't have any overhead and you cannot change, you cannot add gates, you cannot add finite state machines, there isn't much controllability in the attack. So you need to have several conditions to satisfy this attack I mentioned. First of all, you need to have your own user level process to have a specific ID. This doesn't happen all the time, and you need to be very, very lucky. So it's a statistical attack. You need to deploy the malicious hardware to many targets, and you need to force them to use your malicious application, as I mentioned, a game, for example, in Google Store or Apple Store, to have some success. Also, as soon as the address space ID is corrupted, then the new identifier must belong to the kernel. So you need to go from, in the previous example, from 128 to 0. If you go from 128 to 127, for example, or something else, 129, it doesn't work very well. You need to go from 128 to 0. So you need to put the attack in the most significant bit in the previous example. And finally, as soon as you do the context switch, you need to immediately corrupt the kernel function. So there is a timing window that you need to modify this PAL code that is shown here. You need to do it very quickly, put a return instruction in kernel space, and then invoke it to be able to succeed. However, this can happen, as I'm going to show you here in the results. As you can see on the vertical column, these are how many clock cycles it takes to actually gain privileges. So if you have a very heavy workload, it takes less than 10,000 clock cycles to actually escalate privileges. So you have to try it a lot. It's not like something that you can try only once and you have 100% success probability. Here you have to try it 10,000 times if you have other processes running in the system and you have very often context switches. Or if you have only a single process, it takes less than 2,000 clock cycles to gain privileges. So in this context, it is extremely fast, even in presence of other processes. However, you cannot guarantee that you can try only once and you will escalate. And these are some real benchmarks from Spec 2000. In these benchmarks, then the number of clock cycles is increased because you don't have the synthetic benchmark I showed you before, but still it's less than 1 million clock cycles. And finally, this is in terms of the system load. Again, now the number increases to almost 4 million clock cycles, depending on the load of each particular process running in parallel to your attack. So even if you have a system running many processes at 100% utilization, you can still escalate privileges under 4 million clock cycles. So that's the idea that this attack even works under very heavy workload. So in the summary is that it is possible to have malicious modifications at the processor level that have minimum overhead. We only changed the delay of a wire at a very specific point. This was demonstrated as a privilege escalation attack, and it goes through only in a few million clock cycles. And since the attacker only has to win once, the practicality the practicality of this attack is deemed realistic. Now, there is also a second attack described in the journal that I showed you earlier. This is on a different processor. This is the OpenRISC processor 1200. And in this attack, we are leveraging the supervisor signal. The supervisor signal is the signal that tells the processor, go from ring 3 to ring 0. There is one particular wire that controls a special purpose register. As you can see on the top right-hand side, it says SPR. This is special purpose register. And this combinational logic controls the value that's written in that register. So if we can put a fault at the wafer between those two wires, between the supervisor mode and a write signal, then the write signal essentially dominates the selection of the end gate. And what happens is, even though the processor is not in supervisor mode, we are actually triggering supervisor mode by sending a write signal to that register. And here's how this happens. Essentially, as you can see in the right image, you have these wires, and you just insert a fault, which is something that can happen by a dirty mask in the foundry. And now there is a resistive bridge. A resistive bridge means that in a very small percentage of the time, one wire will trigger the second wire. It's like a crosstalk between wires. Okay, and we also demonstrate that in the paper. So I'm just sharing two or three links here. I made them tiny URL so that you don't have to copy paste long URLs. So the journal article that I mentioned is open to everybody. You don't have to be a subscriber to IEEE to download. The URL is tinyurl priv-trojan. There is also an article that mentions this paper and describes a new attack in the analog domain that's very similar. This is tinyurl fab trojans. And finally, there is essentially hardware security book or trustworthy hardware book that Professor Kari has been sharing. And this is in the third link, hardware trust. So these are the three links that you can ignore tinyurl. You just write down priv trojan, fab trojans, and hardware trust. And these are additional resources that I encourage you to read. Especially the second article is only a few minutes read, and it's very interesting. So I guess that's all. I'll pass back to Professor Kari to continue.
Thank you, Nectario. So any questions? You want to mute? And you also mute on this. Any questions? On this, it goes here. Oh, yeah.
This is Alex again. I've got a quick question. Or maybe quick. So we were talking with the first attack that you mentioned, where there's this delay issue, and that you were able to switch the sort of active PID for memory access. Would that compromise other user processes during their context switch? So for example, one with an invalid, not the perfect PID, begins and immediately does a write after context switch. Wouldn't that write to the wrong memory address?
So that's correct. So if the compromise does not fall into kernel space, then when you try to write in privileged memory space, your write will get denied. The processor will not let you write to privileged memory space because the process that you are trying to use is not privileged to access that memory space. So if there are three outcomes, either the attack is successful and you get a ring 0 privilege level and you actually manage to finish the attack. The second option is you get a valid process that's ring 3 and you don't get permission, or you get an address space identifier that does not exist. So again, the attack will fail. But the impact is only going to be to your own process, the malicious process that tries to exploit the system. It will not affect someone else's process, because you are trying to make the system think that you are a kernel process. That's the actual goal there.
Yeah, so I follow you there with our given attack process, but two different PIDs on the system that are just random processes being run. If they're both level 3 processes, the first one could accidentally write immediately after a context switch into the space of the second level 3 process, and therefore make the second process run wrong or have an invalid value somewhere.
Okay. Yeah, I understand you. Yes. So that's essentially a side effect of the compromised hardware. But the idea is that we as attackers, the person who designed the attack is interested in compromising the kernel. But the side effect is that, yes, the processor is broken, essentially, and that can also happen.
Yep. Okay. That's all. I just wanted to confirm to make sure I understood it correctly.
It's not preventing you from preventing a one ring 3 attacking another ring 3 if they know that this exists and they try again and again. Because it's not only limited to the kernel, but it's interesting in terms of privilege escalation to do it to the kernel. That's it.
Okay. Okay, that's thanks, Nectarios. So this is a concrete example. What do you share? Okay, let me share my screen. You are sharing my screen. Okay. Yeah. So that was a concrete example that Nectarios did about 3-4 years ago.
Yeah,
4 years ago. Yeah. So you've been here that long. So. And so it's you see, these things can be done. So the other thing along those lines that we did. So can you see my slides now? I think you can see. Can you hear me?
Yeah, we can see your slides and hear you.
Okay, good. So if you look at so these are the various things that. So if you dig deeper a little bit, you will see the variety of things that can go wrong. So if you're focusing on, let me see. Yeah, if you look at the design phase, you can have malicious standard cells. You can have malicious third-party IP, which is VHDL code that you procure from somebody else and run through the stuff. And if you, at the design stage, there are a couple of other things that the tools themselves could be malicious, and the models themselves could be malicious. So this is what I want you to do. I think Siddharth Garg and Jay Vijayan and somebody else is organizing what's called the Hack at DAC. You know that, right? So you may want to come up with interesting ways of compromising tools. This is the focus of open source tools for placement, partitioning, whatever it is, high-level synthesis, standard cell generation. So that's the focus of that competition. I hope some of you participate. And then the simulation models and so on could also be compromised. So those are the things that can happen at the design stage. Then if you look at the fabrication stage, there are several things that happen. You have the fab interface, you have the mask, the fab itself, wafer probing, and die packaging. So these are the things that can go wrong there. You could have a malicious mask replacing a good mask. you can have some at the fab itself. You can etch things off and etch things on, and focus ion beam based etching, and you can do some things like that in the foundry at the fab. Then and that's the ASIC flow. If you look at the left hand side, from the design, when you go to the synthesis mapping on an FPGA, essentially generates a bit file and configures the FPGA. So you could have a malicious bit file replacing a good bit file, and you can misconfigure the device. These are the two possible things that can go wrong when you go through the FPGA route at the very least, assuming at the design flow level. These things, tools and models are typically, and IPs are common. Tools and IPs are common to both flows. Standard cells are specific to here. Models could be different for both. Some models here, some models here. And you have these attacks here, and you have these attacks here. So that's what you can do at the design phase. So let's also look at the things here. So if you look at the hardware abstraction level on this, you have at the system level, which is C level, and then you have the RT level, then you have the gate level netlist, you have the transistor and the physical level. And if you look at the system level, you can change constraints maliciously. Instead of making high power, low power, you change it, change the power constraints, and suddenly things go wrong. And change the protocol that you use, or make changes to the protocols. And I think I have an example of this, or things like that. I have a paper. We'll send you a paper which I'll tell you where all of this data came from, and then we'll talk about that. So you have gate level Trojans, and we have seen some examples of those. So you can add gates and replace some gates, substitute gates, and so on. And if you look at the physical level, which is essentially wiring and routing and placement, partitioning, placement, and so on, you can modify the layout, you can modify the wiring, make them thicker, thinner, and this and that. At the transistor level, you can size the transistors differently by modifying their parameters. You can some attackers can do that. And at the RT level, you can again change logic. Same with gate level, you can change logic, and so on. So these are the things that can happen in greater detail at the abstraction levels. Then if you look at the system level, I think this is the same as this slide, if you notice, right? They give you, so this is an example of a system where you have a bunch of networks. You can say what protocols go here, and you can alter those protocols at the specification level and potentially not get detected. Because anything that you do at the most damaging attacks are at the system level, where if the specification itself is altered, then everything else matches against the specification or verifies itself against the verification, and there is no way to detect anything. So these things go undetected. At the RT level, you add additional gates. You can change logic. Instead of don't care states can be altered carefully. So and you can do some of those things. And you have seen some of these examples in the tiny examples I showed you, and in the examples that Nectarios talked about. And also, you've done something of this kind in the first lab, right? So so let me ask a question. The first lab that you did, which is automatic insertion of Trojans on an FPGA into one of the designs, can you classify this? Maybe you can send us an email on what you did, a quick summary of classification, summarize or classify the Trojans that you inserted according to this along these 5 dimensions. Vinayaka, you may want to put this on the announcements. So based on the Trojans, it won't take more than a paragraph. So I don't even need a big, just send us put it on the results thing. I don't know how, but I don't want an email, but just go to the new classes and do that. This is at the gate level, you can add additional gates. And transistor level, you modify the thicknesses. I'm just going over this quickly. And then at the physical level, you have these layouts, and you can make them closer, thinner, thicker, and essentially these are called reliability attacks, where you make it less reliable. Okay, and if you look at the Trojans activation, I'll quickly run through this. I'll show you a couple of examples later on. So let me give you a quick background of what we've been organizing. What's called the Embedded Systems Security Challenge, or Embedded Security Challenge, or Embedded Systems Challenge. That was what was. It had all these different names, but essentially it's called ESC every year in November. And we started doing this in about 2008. So at that point in time, there was a couple of Trojans, and we went and talked to DoD, and we said, tell us what kinds of Trojans have you seen? They said it's classified. So they wouldn't talk about it. So what? And then, of course, my students and a group of us sat and figured out a few Trojans. But it's not scalable, because once you talk to me, I think one way, so I can create Trojans that in one. So what we did is we organized this challenge, and we asked people to come up with interesting Trojans. That was the definition. It was very open-ended. And and we gave them an FPGA, something like this. That Xilinx didn't know what they were getting into, so they donated FPGAs for Trojan stuff. So first 3 years, they gave every student or every team that participated got 2 or 3 FPGAs for free. They directly mailed it to them. So we used to give them initially. Yeah, I don't need this now. It's fully charged. So we gave as a design problem, we said insert a Trojan into AES. And we put this AES on the FPGA here, and then we connected it through some of these interfaces to display the results on here and apply inputs through, I think, these keys and also RS-232. So a couple of students actually put AES on this, and also designed the interfaces like UART and everything, connected it there, and gave it to the teams. So they got the FPGA boards, they got these designs. We said insert Trojans, and tell us why these Trojans are good, and tell us why these Trojans are difficult to detect, and tell us why these Trojans will have create the most damage. Extremely open-ended, right? So this was the example platform, and over years changed, but overall. So this is how the plain text came in, ciphertext went out, and then people came up with a variety of attacks. We kept it open, so very open-ended. So one class of attacks was leaking secret keys through variety of side channels that are on the FPGA board. And sometimes these, so then people came up, so this classification that you see that we did in retrospect is quite obvious, but at that point in time was not as clear. So after 3 or 4 of these challenges, after 3-4 years, we started seeing some interesting trends, and that's when we started coming up with this taxonomy. Most people are comfortable making changes at the RT level, and that's more of an artifact of the audience that we reached out to, or the competitors. These were students who had access to FPGA synthesis tools, and people who had students who had access to a few other tools and so on, FPGA board. So they were very interesting. So there was, I always talk about this high school, an undergraduate student from RPI who had zero background in design. We said, so he did some Trojan insertion, and then we said it has to be undetectable. So what he did was he hacked into the Xilinx tool itself and made it report the good numbers. It never reported the bad numbers. So it was just the visual interface where, you see all these CLB, slices, all of that. That particular hack was on the CAD tool, which essentially, he was inserting this huge Trojan in there, mux and this and that. But the reporting, but the FPGA reporting tool was just saying the same numbers for the original design and gave the same numbers for these Trojan design. So that was an interesting attack. And so these are the things that we started looking at uncovering, and that's how this classification came around. So internal triggered and so on. So time-based, people started putting in some control, some loops, counters, and so on. So physical condition-based was interesting too. Somebody was running ring oscillators and measuring the temperature and using that as a way to trigger Trojans as well. So that was demonstrated. And then cheat sheets was quite popular. People would give, and the way the cheat sheets was interesting too. So it could come through RS-232. I'll show you an interesting way of. I think I have it somewhere. But then you also can do it at multiple locations. People have demonstrated all of those. I'll quickly run through this. Nothing exciting about it. You can read through the slides. So the thing that they did was change function, change spec, leak information, and all that stuff. So this is what Trojans were submitted to Seesaw, and this validated the taxonomy. So so I'll show you 3 examples. When you see New Haven, again, this is a team that was from Yale, and they were doing that. So this was the cheat code that you had to enter. So you required physical access for the attackers. Input triggered Trojan. So this was the summary of the phase. It was done at the design phase, the abstraction level. They inserted this Trojan at the RT level. The activation style was user input. The effect was when it saw this, it started leaking information, transmit the encryption key without being detected. On some of the, as part of the existing protocols, it was doing something interesting, and its location was in the processor and I/O because it had to leak the key. It was using the I/O. The I/O, I don't know if this is the specific example, but they were flickering these 7-segment displays, and if you carefully look at it, you could figure out the key and so on. So they had interesting things there. They also did the denial of service attacks. So we've seen all of those based on a particular key. So what they did was they redesigned the original design, so this was interesting because they reduced the number of flops in the design by making some changes. So they saved on some of the flops and used the saved flops to create their own Trojan. Then it's difficult to figure out, right? Because it's doing the same functionality. There was no overhead because you initially created yourself some margin, and you use that margin to hide the Trojan. Again, this is a summary. They were doing this during the design phase, RT level. Activation was the user input. Effect was denial of service. Again, processor and I/O, what the locations were. This is something else where they were monitoring the chip communication channel and replacing selectively the messages that were being transmitted. I think you've seen enough of those. This is how you can so this is what I want you to do for the Trojans that you inserted for your first lab. So a summary like this. Explain what something like this and a summary like this. One slide. In fact, if you can give me a slide of this, I will add it to my presentation next time. That's how I keep making my slides denser and thicker the slide decks. Okay, so you can do buffer overflow. I won't talk about it. I think it's a whole lecture by itself. There's a buffer overflow and some return-oriented programming and control flow attacks. I'll talk about them, or maybe sometime, and I'll skip that. So this is an interesting protocol. So I wanted to. So this is a simple transmission protocol that was operating at 9600 baud. So when the receiver monitors this protocol at 9600 baud, it sees these. This is the duration of each bit, B0, B1, B2. Huh? Yeah, did somebody raise hand? Did anybody have a question? Yeah. Maybe it's because of my screen. Okay, anyway, so this is the normal operation of the transmission channel. This was the small normal rate. Now imagine running this at a faster speed, 19,200 baud, right? Then you still have the same things, but you create for yourself some space to insert some covert messages. We call it KRO, but there's 7 additional bits, so you can double the thing. So if your receiver is tuned to this baud rate instead of this, then it can read this message, which includes the original message as well as the subliminal covert message. Here, if the normal channel is this, the normal receiver will operate at this rate, and it will get the normal thing. So a normal mode this way, attack mode this way, that's how you can transmit stuff. So this was an interesting demonstration. As you notice, all of these are very weird Trojans, and not a single person could not sit and come up with all these different Trojans. And this is what we did over the last 10 years and continue to do, crowdsourcing of Trojans and all these threats and all these vulnerabilities. And we moved on to, initially it was on AES, then we moved on at some point to a processor. That was when the privilege escalation attack and a variety of other attacks, this was, we gave you an 80,
I thought it was Thales had the processor and 8085.
So we gave an 8085 microcontroller to attack, so they did this privilege escalation attacks, and or
they were
precursor of privilege escalation.
One instruction code in parallel
to stuff, and then we also did in one. So at some point, somebody had to give these challenges, and that was getting challenging. It was getting boring. I mean, it took a lot of preparing these designs to be subjected to attacks was getting a challenging, was time consuming. So initially we put out the challenge, they would hack the design. We put out the design, the competitors would hack the design. But after 3-4 years, people started getting press, and people said, can you figure out, can we use our defense, whatever the defense is for a particular, can we put this, and can people then hack and basically red team the defense? So at some point, I think 4th or 5th time around, University of Connecticut came up with some techniques. They said, oh, we have good defenses for a particular threat. Can you use this as an ESC? So people were able to undermine some of those defenses. So they learned a lot. So that they were the blue team, and the red team was the competitors. And then a couple of years later, so that continued for a couple of. Columbia said they had this fancy defense. It's called fancy, where they put Trojans in very lightly active regions of the circuit. Some wires don't trigger that much, and they're hard to detect, so they put in there. So that wasn't. But then at some point in time, we played this game slightly. Initially, we were the red team, blue team, and the crowdsource, the participants were the red teams. But for some time, we also switched. For half the competition, for somebody had to be the blue team, and then for the second half, they had to be the red team, and everybody puts in their hardened designs, and everybody hacks somebody else's hardened designs. So we played this game, and then again came up with some interesting results. And so we did this. We collected about 1,000 benchmarks, by the way. These are all on what's called Trust Hub. So I'll quickly go through this. I think you'll see a bunch of, you can see the slides. This is one summary. You can see this from the, you can't read anything, neither can I. I don't expect you, just to show off that all these crowdsourced benchmarks that we collected essentially informed the classification, the Trojan taxonomy that we derived. We just didn't start off with the taxonomy. So, and we made some changes, and so this is quite. So if you see this picture, usually you see that. So you see that picture quite along the taxonomy in most places that work on Trojans. So combinational Trojans, quickly you saw this. Sequential Trojans based on counters with a K counter, and so these are the, you can calculate the probability that they get detected, right? quite low. So that's the taxonomy for insertion of Trojans. The next question is, how do you detect them? And you could first do non-destructive approaches, peel off the chip and see if there's anything wrong, right? And then it's like, this is a good job to have. If this is like a cookie taster, right? How do you know? You got to taste every cookie before you know that that cookie is not bad. It's good and bad. So because Trojans need not be inserted in all batches of chips, so you got to so you got to do some random sampling, or if you are much more aggressive, you got to do on every chip. And destructive is not a good idea, right? Because once you destroy the chip, once you eat the cookie, even if it is good, there's nothing to sell. So then you go to the non-destructive approaches. There are two kinds there: continuous monitoring, and that which is online, and runtime test offline, which is test time detection, where you find out additional test patterns that can detect these hard to detect faults, right? That's what it is in tech. So typically, these Trojans are inserted in locations that are difficult to reach via tests or test patterns. And in regular testing, they would give up and say, oh, it's not important because likelihood of doing it. But here, that's where the attacker would go. He will go run the test and say, oh, this region is hard to test. Let me put a Trojan there, right? And you could also do a couple of things. This is regular logic testing and make it easy to test and make sure that you can reach all the corners. The other thing you can do is monitor the side channels. Are the side channel signatures anything different? That is the power side channel, timing side channel, heat, thermal side channel, EM side channel. So you can look at multiple side channels. Use them as a way of detecting any changes in the specification and so on. So those are the two popular classes. And then you can put preventive and isolation and so on. So this is what it is. Then this is in prevent. What you do is this is where we talked about logic encryption and camouflaging. If the attacker does not understand the design, he would not be comfortable inserting something malicious in the design. So that's where your obfuscation technology, or in logic encryption and camouflaging all come into play. And then